First, it should be sufficiently randomized over this period of 2 minutes. And if you're having this, then you should see kind of always there's some degradation because somebody is always computing routes. But you should not notice that that the entire network is becoming at sometimes appears to be overloaded and then it goes away. So what happened is that the routing messages led to an effect where all routers synchronized to do the route computation at the same time. Yeah, and then the people studied that, and they saw that this is something like a critical phenomenon that happens at some, if you're putting enough routers together. It's the same phenomenon that some people observe if you're putting analog clocks, put them at the wall, that turn out to self-synchronize. Yeah, there's some effects that take place. I don't know if you heard of it. Anyways. So that's about something else about routing. Many anecdotes about routing. Let's see. Type of service routing is allowed. So what one can do is one can do routing based on the second byte of the IP header, the type of service field. Yeah, we call it the diffserv field. The type of service is the old name for that field. Subsetting, multicasting. It also allows hierarchical routing. That is something interesting. It allows to have structure, and that is why people in organizations like it, because you can have branch routing and then some backbone routing within the organization. This is called areas, and it's actually, I don't know if this is a deleted part, but it's in one of the experiments that you conduct in lab number 4. Anyway, so for a network like this, so this is the view that routers have. You see here we have pretty much routers have names. It's one of their interfaces. Each link has a name, which is just the configured interface. Like this is here the network, and then the link here has going to be .1, and this router has to be 10.1.2.1, and this one here has then 10.1.2. Yeah, so then link costs can be configured, and you can have costs, in different directions. So because it makes sense because they're configured at the router. I configure my cost, and you can configure different costs. Yeah. So the metrics are, numbers here, 65,000. So, as I said last time, there's a link state database. That's what link state routing algorithms do. So each router should have, the goal is to establish an identical link state database at each router. So each router has a complete map of the topology of the network. So when the routers discover each other for the first time, router comes up, I have an interface that is up, I send out a message, the OSPF routing process sends out a message, it's called hello, on this link. If there's another OSPF router receiving it, it responds with hello, then they make a handshake, and then they exchange their link state databases. And then kind of the link state databases are then sent using a mechanism called reliable flooding. So in this case here, so reliable flooding looks like this. Flooding is a process by which, like a broadcast, a simple way to implement a broadcast, very wasteful, however. Reliable, so what it means is a node sends the link state advertisement out, then reliable flooding means for each message received, the message is sent out, flooded on all outgoing, on all other interfaces. Yeah, so if this message gets received, then it is sent out. So this router sends it on this and this one sends the link state advertisement over here. Yeah, so that's flooding, which means flooding always comes with a lot of duplication. Yeah, like this. What we're having, the link state advertisement came from here. This, the router here sends it to the one on the right and the one down. The one down here sends it to the one up and to the right. So, it's receiving essentially 2 copies. And it goes on in this way. Yeah? Reliable flooding means that for each transmission, there's an acknowledgement. That's just at the level of the routing protocol. Send a link set advertisement, I want an acknowledgement. If I don't receive it, I resend it. That's the reliable part. And then, update the database, and so it goes on, and that is then done through the entire network. That's what I said. Everybody receives the complete topology information. So after this reliable flooding, all routers know about the links of this node. That's the global dissemination. And every router has to do that. Yes?
So I'm just wondering, for the acknowledgement, does it expect acknowledgement from all routers in the network?
No, it's point to point. Yeah? So it's it's only by the center of the flooding. Yeah? I send it to you, you act to me, you pass it on to the rows behind you, you expect X from the guys who you send your data to. Yeah? So just neighbor by neighbor. It's not, that would not work.
Yeah.
Yeah? That would be having everybody send acknowledgement to a single device. By the way, the scope of routing. Link state, so OSPF works up to few hundred routers, not more. That's it, yeah? So, links, that's the limitation of, because this flooding operation just takes over and consumes too much bandwidth. So, but networks don't tend to exceed that size. Intra-domain routers, networks don't have, are generally not large. All right. Okay, so got this. What else can we talk? What else is there? The message. Yeah, well, so OSPF has a message format, and the OSPF message has its header. In the header, you're sending link state advertisement. A link state advertisement has a header. So it's this is where the link state advertisements are standard. And now what is different? This is of course trivial. Yeah. So OSPF has an IP protocol number. If you remember, RIP used UDP to send data, so it used the UDP port number, and so it used the protocol number of UDP. At the IP level, OSPF is a real data link layer protocol. Let's see. The TTL is set to 1. Yeah? TTL meaning that routers just talk to the routers one hop away. You need to disseminate, and that router will disseminate it further. But the router does not send. OSPF routing messages are only exchanged between neighbors in the topology. That's what this means. What else? Yeah, so here this is the. There's some. So different types of messages. I go through an example quickly with a hello, a database description, link state request, link state update, and then the link state acknowledgement. Yeah, so that's how this goes. What else? There is authentication. So there are actually, there's also clear text transfers and something like that. There are actually authentication schemes that use that are better than what is provided in RIP. Yeah. At the same time, I don't think that routing messages at UFT have any kind of security in them. Yeah.
I have a question about the previous slide, actually, about a few of the terms on it. So, SPF routers, I understand, but what are the V routers? Are there domain routers? Anything in the front of the OSPF?
Well, yeah, I don't want to go into the OSPF has some concepts called designated routers. Yeah? So if you have multiple routers connect to a single subnet, then one of them is responsible for getting, one of them acts as the router. Yeah? That is, and there has to be an agreement process, kind of like some kind of agreement being reached who that router is. That's the designated router. This is just the whole group of all routers on the network. So this is, if you're sending these messages point to point, So this only is the case if you have your local area network and multiple node routers are attached to that. Right? A lot of details on OSPF. There's also this issue with the areas that which you explore in the lab, which I won't talk about here. Let's just do, link set. And this is how the link set looks like. Link ID metric. Here's an example exchange of a router. So here's an example of a scenario where this router 10.10.10.1, is that the router? Yes. No, 10.1.10.1 starts up talking to another router. Yeah? So this is here how routers exchange. The first thing that routers do, like this router here, this router here was rebooted, 10.1.10.2. It reboots, sends the hello messages to the other router, the other one responds. So that means they have discovered each other. They're adjacent. Then they're doing this exchange of their whole link state database. Yeah? So router LSA and adding some sequence numbers to it, and that's essentially what is taking place. Yeah, so it's the only thing that, so you discover adjacency, one guy sends the database, here it's empty, so there's nothing in there, the router that's there sends its full database, and then they continue to exchange it, yeah? So this is how it looks like. What can I say? That's now at the protocol level not so interesting. The interesting part that computes the shortest path is done with this link set information. The router OSPF, the routing for the daemon, the routing process running on the router needs to collect these entries, create a topology, run the shortest path algorithm, set the routing table, and that's it. You see, that's why I want to talk more about OSPF. Good. Let's move on to greater things. So what you take away from this here is two different kinds of protocols. Link state routing preferred, not with disadvantages. Link state routing, there are scalability issues inherent. Okay, next topic is the border gateway protocol. So first have a longer section on inter-domain routing and the principles of it. Then, probably on Monday, we'll talk about BGP. Now, what I talk about here goes a little bit beyond what you normally find in textbooks. Because not in textbooks, people don't explain, talk about networking books. They don't feed a lot of insight into how inter-domain routing works. They focus on the protocol piece, like OSPF. There's a lot to know and appreciate about what is going on with inter-domain routing. And I try to convey that here. So what I do, this lecture is based on a tutorial by a BGP expert, Tim Griffin. He actually left AT&T Research, he's now a professor. Last year or so. He gave a tutorial on the operation of the border gateway protocol. This lecture is a little bit based on that. Okay, so this is the internet infrastructure. You see a similar picture, but not this picture. So it's essentially what distinguishes different kinds of networks. There are networks at the end, campus network, corporate networks. They're just using that's where the data, where the instances of data sit. Then there are networks, internet service providers. They are carrying network traffic that they did not themselves generate, so they carry traffic. There are different tiers of such network. Tier 3, Tier 2, Tier 1. Tier 3 generally refers to small internet service providers, like local ISPs, small town, city. Tier 2 networks are typically regional networks. Ontario, Mid-Atlantic, California. Tier 2 networks, they cover multiple cities, really are a larger operation. Local ISPs may consist only of one router in the basement. Yeah, that somebody that runs a small business on. Okay, so now these Tier 1 ISPs are actually very well defined. Tier 1 ISPs, there are only around a dozen Tier 1 ISPs that exist worldwide. There's none in Canada. Just because of the scope. Yeah? That doesn't mean that it's nothing that Tier 1 has a certain definition. There's a requirement that we will see is that all Tier 1 networks must have a direct connection to one another. There are 10 ISPs, they all must be directly connected. Yeah.
I mean, if one is in Europe, how is it directly connected to the one in North America?
I'll get to that. I try to get this. These are the right questions. What I want to do is give you views of the network that's set that in place. The Tier 1 network can be worldwide. They must be directly connected somehow. There are different kinds of connections. There are connections, like a connection like this. Yeah, this one here is a corporate network getting a service from an ISP. They access that service somewhere. Yeah, there could be a cable being laid out. But there's a point where they access the regional network. That's their point of presence. So they access the service. A local ISP also accesses the service. There are kind of places on the internet where network traffic can be exchanged between ISPs. These are the internet exchange points. These are public clearing houses for internet traffic. There are many of them that exist. There's one in Toronto.
The one on Front Street?
That's the one on Front Street. That's one of the roads of the building on 153 Front Street. Yes, so these are clearing. These are the clearing of network traffic. This is something where all ISP all these service providers essentially put a piece of equipment, and the equipment, then they put a router in there, and the routers are then connected by some high-speed local area network. There's another way that networks can exchange traffic by a direct link. These are private peering points. The exchange of traffic through an ISP is called public peering. The point through a direct connection. Now this is something where you're having, think about it, you have a carrier hotel. This is a building that houses equipment for multiple companies, and they just essentially run a wire between their equipment, between their routers. And it all goes through the basement somehow, but essentially they're connecting one router of ISP 1 with another router from ISP 2. This is directly between them. That's private peering. All right, so here's a little bit of the language. Locations where networks get access to the internet are called POPs, point of presence. So if U of T accesses the Canary backbone network, there's somebody who comes in, where's your POP? The POP is down in 156. That's where U of T gets its access. The locations where Tier 1 or Tier 2 network exchange traffic, they're called peering points. For Tier 3 network, one really does not, these are small ISPs, one really does not talk about peering. Peering is kind of like a peer relationship. Campus networks and corporate networks are like customers to some other provider, or to some, there could be a provider. Campus network can be a customer to a local ISP, which is then a customer to a regional network. A local ISP is always a customer to some regional or even maybe a backbone ISP, but normally it would be to a regional network, having a customer relationship. Tier 2 and Tier 1 networks can have, Tier 2 to Tier 1 can have a customer-provider relationship, but they can also have a peer relationship. Peer means they're equal settings. Very important for the business of the internet. A peering relation means there's no money exchange. Generally, the ISPs that have peering relationships do not pay each other for that service. I say normally because that's the exceptions to everything, and some of these things are not public. Customers always pay. So, like you're paying, normally you're connected to a typically local ISP, like an access network. Access network of Rogers or something could be which Rogers is pretty much modeled, the boundaries then between local and regional network are modeled. So you're paying your customer at the local ISP, and the access to the regional ISP is paying here. The regional network then either peers, if it does it in this way, does not pay. If it has a relationship that does not go through public peering points, can have a customer relationship. There's public peering places. This is where traffic is exchanged in some, at these internet exchange points, and there are private peerings. Two networks just establish a direct link to each other. And just like you're doing in the lab, it's just connecting one company, making a connection between each rack. Being a company, you do peering by just establishing a link between them. That's essentially technically what's going on. All right, so this is how these internet exchange points look like. So there's this building, nondescript building. Some of them have a few windows. They tend to be highly secured. So they tend to be the most secure buildings that you can find, which are not government and not military. Very difficult to get in. They have multiple checks of IDs, and they can't just run around and being escorted. So these are actually badly taken pictures. Actually, I took these pictures. This is actually where this is taken down here in Front Street. This is a rack of equipment. You see here the fiber optic cables. This is where U of T has its wire going into, if you pull at U of T into the research network, and the cable gets. So that's kind of where it connects. So that's where, and there is a network fiber essentially being laid out to that point. So U of T has a commercial provider and a cogent, and it has for academic traffic, it connects to Canary. This is the room. This is actually operated not by Canary. It's called Orion. It's a regional and research network that connects the research and universities in Ontario. Orion is just, organization that rents a room in this carrier hotel. The room is just one very small, pretty much this width maybe, yeah, like the length of the board here. Yeah, and there's just one rack of equipment, not many, yeah, and that's just is a big node of the Canary network, connecting pretty much directly to New York, Chicago, connecting to other universities in the Orion networks. Yeah, these are point-to-point links, and then kind of you're having your data link, your routers, as well as then what you have is this kind of a physical layer of optical transmission using that wavelength division multiplex. That's how this works. Yeah? All right. Now, how does a backbone network look like? Yeah, so if I draw a picture like this of a tier 1 ISP. So this is the network of a tier 1 ISP. This is AT&T. This is AT&T backbone network in the US. So if you're taking the view of an autonomous system, you just have this one cloud. This is how it really looks like internally. And what it means is that they have these points of, they have these POPs here. This is their point of presence. This is essentially all these big these big boxes. So these are their main locations. This will probably be in some carrier hotel. So carrier hotel looking like something like this. Yeah? Building that is full of telecommunications and IP router equipment. Yeah? They're all throughout everywhere. There are some connections to outlying points that have smaller bandwidth, like just to give you the speed of connections. The red links here are DS3. That means they operate at 45 megabit per second. The blue ones are OC3. This is 155 megabit per second. OC48 is 2.4 gigabit per second. And OC192 is 9.6 gigabit per second. This is the standard from 2000. Today this would be scaled up by an order of magnitude. Roughly, the picture looks like this. Then you're having a few long connections, and then it's panning out. Let's see. Yes.
Is there any OP192 connection on the map?
Is there? Maybe not. Maybe not. This one right there. Okay. And this is between Cambridge. You see this Cambridge and New York, Boston and New York. This is AT&T's global network. Yeah? So AT&T, what I showed you before, is just the US picture. This is their global network, so they are represented everywhere. And this is just one one autonomous system. It's one network. When we route between autonomous systems, this just appears as one bubble with one autonomous system number. If you're going through this network, suppose I go from one autonomous system to the other. If I say like this, in this picture, I go from this network to here, then I cross the backbone network. It looks like I'm going through a single node. What may be the case is that you're going here on a long path through that network, and you may end up entering the network, AT&T network, here in Santiago de Chile, and come out somewhere here in Johannesburg. So, passing through a dozen routers, which are visible by doing trace route. So you can see what's in there, and that's what we found. If we did trace route, we find multiple. If you're looking at the DNS name of the trace route, you can tell which networks you're passing through. Yeah? I should actually maybe do that. Let's see. let's have something interesting. What is interesting, we ask? Something that is remote. Australia. You have something in Australia? New South Wales University. Yeah, that's the university in Sydney. Sydney EDU that. Just let's watch what kind of networks we're going through. If you can see this, Toronto, then GTANet, yeah, GTANet, that's the Greater Toronto Area Network that connects the universities here. Then we're here in Orion, that was this room down in from there, we go to Canary, that is the Canadian Backbone Network. And then we just have, we essentially pretty much crossing Canary, VNC probably, you see here, you can see it from, let's look at the third line, Calgary, so we are here in Toronto, Orion. Yeah, that's when we're still in Front Street. Then, in 3 routers, we're going through one ASP, that's the Canary Research Network. In one, I don't know what the 205 is, the next one is obviously Calgary, the next one is obviously Vancouver. From Vancouver, the next one is in Seattle, Washington, Pacific. Yeah, we're going through another ASP. From Washington, there's a direct link then to AARNet, yeah, probably Australian Advanced Research Network or something like that here in Australia. Yeah? You're happy? High pops in Australia. And then we're just going there. You know, the usual thing is, you know, you're going then into a regional network there. USY EDU, which is already University of Sydney. They're going through their various internal VLANs, and then, you know, let's do something, let's do commercial. Let's do www.microsoft.com. So here our traffic takes a different. We've also got GTANet, but then you're going here through, you see the Toronto Internet Exchange? That is an ISP. Yeah? So that's where traffic is now passing from the domain of non-for-profit research networks into exchanging traffic with kind of phones and the public commercial network. And the network you're going through is so you're going directly into the Microsoft network. That is what you're seeing a lot. I mean, yeah, so yeah, these things one can talk about for long. We're going to talk about this a little bit longer, yeah, because ultimately this is the fabric that ties together the internet. So what you're seeing these days, now this is an example. Google carries a lot of traffic. They're running their own networks, like a shadow network. What Google does is, it does not go, Google has its location, they don't go through the public internet a lot. What they're doing is, they go directly connect to local ISPs, then go into separately in a Google infrastructure, which then connects to their data center. So that Google's traffic does not compete with other traffic on the public internet. Yeah, and these are very large percentages, in the order of 50% of Google's traffic I can't get the real number because I heard it just a few months ago. But I don't recall the exact number now. But it's a significant percentage, like 60% or more, is of Google's traffic does not go through the public internet. It just goes, you're here at home at your ISP dialing in, your local ISP has some link to Google's equipment. Google is offering that. Here, connect to this, which is good for the ISP because there's less traffic that it has to pay for, less that it's being charged by regional service provider. Google provides that for free. Then the network is then going into Google's network, and which is then not touching the internet at all. Yes?
How does Google bring that direct connection to the ISP?
How they're bringing?
Direct connection to the ISP?
Well, that's pretty much infrastructure. They're just stitching it together. Yeah. So they're not digging. Cables are on the ground. It's like something you can rent and lease. An ISP will have, they will just make sure that they get the wires. Once you get the wires, so the question, how does U of T connect to Front Street? That's using fiber optics that are in the ground. That's paying for those. There is a lot of infrastructure in place. You can go to Bell and just ask for, I want to have a fiber link in this, or just an Ethernet link in this room that connects to a downtown center. For enough cost that it can be provided. So that's the infrastructure of the wiring, physical layer. Yeah, that is also a service and a large stream. All right, let's see. I'm talking my way through this here. I think it's important to have that picture in mind. Yeah. So next time we're talking about interdomain routing. Yeah. So what I've shown you is when we route between autonomous systems, where we're saying we're going here, this autonomous system goes to autonomous system 2. These autonomous systems can have locations everywhere. So you really don't know what the underlying structure is. Yeah? So it could look like this. If these are the routers, can be, the physical layout can look like this. But through all of this, there's a lot of structure to the way in which routing takes place. And the routing pretty much goes like this, kind of very simple. You're going up the hierarchy and then you go down. You go up the hierarchy and then you go down. You go up and then go down. You go up and then you go down. So it's kind of this custom. This is relatively few, small number of autonomous systems which are traversed. You essentially go tier 3, tier 1, tier 3, tier 2, T1, tier 1 maybe to another tier 1, and then it goes down. That's pretty much it. You don't go down to regional and then again to tier 1. Anyway, so we continue this and make this technical. Essentially what I'm going to do is talk about the client-server kind of terms like transit, customer, provider, and tiering, things that are